Hi everyone. In this video we will see the electrical equivalent circuit diagram of an induction motor. So we will see that how a physical motor gets its electrical circuit diagram, which will be handy for us to find out the torque generated by an induction motor, and also how the rotor resistance becomes a function of a slip while deriving the electrical circuit diagram, which is a very famous interview question also, that how resistance being part of your, or it is being function of your slip. So let's tune. So we know that the induction motor has two circuits in physical model, which is the stator and the rotor. And the stator has the three-phase winding, which is being used to create the rotating magnetic field in the air gap, or the electromagnetic flux, which we have seen in the earlier videos also, that how the RMF is being created by the stator windings, three-phase stator winding. Also, we have the rotor, which if you talk about the squirrel cage rotor, so it has the conducting bars. So both the stator winding and the rotor conductors will have their own resistance and the reactance. So here this model is specifically shown over here, the per phase. So R1 is the per phase resistance of one phase winding in the stator. So here I have taken the resistance in one phase winding as R1. Similarly, the reactance of it is shown by X1. This parallel circuit represents the phenomena which is being used to create the electromagnetic flux. So here this accounts for R1 and X1 accounts for the losses being happening in the stator, whereas the parallel component is the magnetizing equivalence from the stator winding. So RC and XM is the magnetizing reactance, whereas similarly the RC is the resistance which is being offered during setup the electromagnetic field. And the magnetizing current IM here is the current which is taken by the induction motor at no load also, which is being used to set up the electromagnetic field in the motor itself. So therefore we have this series circuit which is shown by here R1 and JX1, and in terms parallel equivalence it is being used to represent my magnetizing component of my induction motor. So if there is no load on my induction motor, so I can say that the induction motor will draw only the current IM, and this current I2 will be equals to 0. So I can say that during the no load operation, the current drawn by the motor, which is IM, and very of course that is equals to I. So the supply current which is being drawn from the drawn by the induction motor will be equivalent to my magnetizing current, which is being used to set up the flux inside my motor or in the air gap itself. And here the E1 is the induced voltage by the stator windings in the air gap. So this is the induced voltage which is being set up by my stator winding due to Faraday law of electromagnetic induction in over the stator windings. So I hope it is clear that how the stator, the physical part of the stator, is being represented over here in terms of the mathematical model. And as we know that these series things R1 and X1 accounts for the losses happening in the induction motor over the stator, and this parallel branch accounts for the power is being used or utilized to set up the electromagnetic field or the flux, magnetic flux inside my air gap or inside my motor over the air gap. RC stands for the core loss resistance. It is just like the transformer, where it is like if I want to establish the flux and my windings are being placed over the magnetic poles, which is being uh, modeled in my motor. So that poles are simply being formatted or is being made by my uh, material. So that accounts for some kind of a resistive loss. So that is being accounted as a core loss. And this is fixed. Instead of this component is being fixed, it does not depend on the load. It does not depend on the load on my induction motor. So whether the increasing load or decreasing load over the rotor of my motor will not going to fluctuate the value of Im or the losses or the power consumed to establish the magnetic flux. So it is independent of my load segment. All right, so now we can talk about the stator. We have already talked about the stator. Now we can go for the rotor circuitry. So as we know that this voltage is being produced by the stator winding, and the rotor induced voltage, let's say I'm taking that as ER here. So that will be equals to, and it is a function of the slip. So S into ER naught. So where ER naught is nothing but the standstill rotor resistance. So I can say that this is the standstill rotor EMF, induced EMF. So if my rotor is at standstill, that says that my slip is 1. So in that case, the the EMF over the rotor will be equals to the standstill EMF. So this is the function, the rotor EMF is the function of the slip. As my motor starts rotating and as the slip uh, gets it decreases with respect to the gaining of the speed by the rotor induced EMF will also get decreased. And similar to my stator, we have the rotor resistance and we also have the rotor reactance. Here we don't have anything something like the stator which has the parallel equivalent circuit diagram like parallel branch over here, because the magnetizing component is being done by the stator itself. Or I can say that to produce the electromagnetic field or the magnetic flux, only the stator winding is being used. The rotor don't have any part to do that. So therefore, we have to account only for the resistive drop and the reactive drop or the reactance drop. So therefore, XR represents the reactance, and similarly the RR represents my rotor resistance. Here again, we know that the reactance is a function of the frequency, so 2 pi fl, where L is the inductance of my winding and the inductive reactance XL becomes equals to 2 pi fl. So we know that this is the reactance phenomena, and we also know that the rotor frequency Fr again is a function of a slip. So Fr is nothing but the slip time of the supply frequency or the stator frequency, because the same is the supply frequency is the same as the stator frequency. So the rotor frequency again is a part of my slip. So therefore, my rotor reactance XR will also become a part, or also will become function of my slip. So I can say that XR will be equals to 2 pi and the frequency Fr will be equals to S time of Fs into L. So I can say that XR will become equals to S time of XR naught. So here again, XR naught is the standstill reactance of my rotor. So this is again standstill reactance of my rotor. Standstill reactance. So again, if the rotor is at standstill, it is not moving, slip becomes equals to 1, and the reactance of my rotor will be also become equals to the standstill value, which is XR naught. And as the rotor picks up the speed, the S goes down or the slip gets reduced. Again, the reactance of my motor gets reduced. Keep this phenomena into the mind, because we are going to use this thing a lot while deriving the starting current value, also the torque value at standstill, and other values. So this concept we are going to use it further. All right. So we have modeled both the stator circuit and the rotor circuit. Now let's combine both these two mathematical models into one so that we can have a complete equivalent circuit for our induction motor. So as per the previous circuit diagram, I can say that if I want to find out the current drawn by my rotor circuitry, let's say the I2S, I'm saying it, so that will be equals to, simply I can say that it is the rotor EMF ER divided by the rotor impedance Z2, and both are the functions of slip. My rotor EMF is also function of slip, we have just seen. Similarly, the rotor impedance is also function of slip. Just now we have seen that how the reactance also depends on my slip value. So therefore the current drawn by the rotor will be also a function of slip. So putting this value, we have seen that ER is the EMF of the rotor is equals to the S time of my standstill EMF of my rotor. Similarly, the Z2S becomes equals to the S time of my X R naught, the standstill reactance into slip, and plus the R R. RR here is the rotor resistance which we have taken into our previous electrical circuit diagram. And making it square of it and taking the another of it, so it is nothing but the amplitude, or in other terms we can also write it simply S into R naught divided by RR plus J of S time X R naught. So here clearly it is shown that how the current I2S is the function of my slip. So here in the numerator also we have the slip, and the denominator in terms of the reactance also we are having the slip value. However, if I want to just replicate or just want to compare this model with the transformer, because both the transformer and the induction motor works on the same principle. The only difference is in the transformer the secondary circuit is the stationary, whereas in the induction motor the secondary circuit, which is my rotor, is the rotating part. So therefore, due to this rotating function, the current is also becomes a function of the slip, and similarly the other values also become the function of the slip. However, for the simple calculation and for the simple approximation, if I want to develop my induction motor model just like the transformer, or in other terms, this we need to understand, it is something like very complicated. If I want to consider my rotating rotor as a fictitious stationary rotor, just like the transformer. In the transformer, the secondary circuit is uh, stationary. However, in induction motor, the rotor is rotating, very obvious. But due to the simple calculation or for the simple approximation, if I want to consider that the rotor, if I want to bring that flavor into my equivalent circuit diagram, so I have to show that the rotor is the fictitious stationary part. Let's assume it that it is I'm taking that it is something like the it is not rotating, or let's say bring it down that it is something like a stationary secondary circuit of my transformer. So how to do that? So to do that, let's simply say that I'm dividing this I2S denominator and the numerator with the function with the slip. So my expression becomes simply ER naught, which is the EMF induced at the stationary, just like the transformer, right? And simply J and S gets cancelled. X are not, simply like the reactance of my secondary circuit, uh, similar like a transformer. So the reactance is also seen here is not part of my slip now in this case, and the rotor resistance divided by S. So looking at these two things, one we have the two expression for the rotor current. One is this one, other one is this one, and both are the same. Both will give me the same value. However, for my equivalent circuit diagram, this is something like I can say that my rotor are the induced EMF, just like the transformer approximation. The induced EMF which is being done by the primary circuit is the same, similarly like I'm getting at the secondary circuit. If I have taken the voltage ratios, let's say 1. So whatever is being developed by the primary circuit of the transformer, it is being transferred to the secondary circuit. So we don't have any function of the slip over here. So we don't have anything over slip over here. Similarly, the reactance is also it's not part of my slip. The only thing which is varying is the resistance of my secondary circuit, because it gets function of the slip. So that I can easily correlate with my transformer equivalent circuit diagram, where the secondary resistance can be varied by the external, let's say if I applying the load, then the secondary load is also getting changed, and then the resistance is also getting changed. So this is okay for me. So here, why we am doing this, or why we change, or why we take such kind of a thing in our equivalent circuit diagram, just to replicate my rotating rotor of an induction motor, representing as an 60 years stationary rotor, just to have the approximation like a transformer. I hope it is clear. Let's go further. Going further over here, now it is simply what we have developed: rotor stator resistance, reactance, having the magnetizing component over here, whatever is induced by the stator winding over here, and then we have the rotor induced EMF over here, and the rotor reactance and the rotor resistance. So this is, it does not have any approximation with the transformer, because we are considering again same the slip concept. However, here this is simply like the approximation uh, or the similar equivalent circuit diagram, just like my transformer. Here I have shown here that x2 is not a function of my slip, whereas the resistance of my rotor part becomes the function of the slip. So therefore it will be a varying function, and whatever I am developing over here over the stator winding, same is being transferred over my rotor. So this becomes my A1 if I'm taking the voltage ratio 1, just like in the case of the transformer. So same thing will also get in the case of the transformer. So the only purpose here to show the rotor as a function of slip is just to replicate it with the stationary rotor, just like in case of the secondary circuit of my transformer. However, we always need to keep in the mind that rotor of the resistance of the rotor does not depend on the slip. It is constant. The reactance gets vary with respect to the slip. It is very obvious. It is the generalized thing. However, to make it the equivalent circuit diagram, here we are showing, or we are ordering our equation so that we can compare the induction motor equivalent circuit diagram with my transformer equivalent circuit diagram, just for a simpler approximation and the simple calculation. I hope with this video it is clear. Two things: one is that how to model a physical thing into the mathematical expression of the mathematical modeling, and the second, which is the very would say famous interview question, that why the rotor resistance gets function of my slip. It is just to simply represent my rotating rotor into fixed years stationary rotor. Okay, thank you.